Number one, student A conducts an experiment to determine the speed of sound in air using tubes of different lengths. Each tube is open at one end and closed at the other end. A short pulse of sound is produced by a loudspeaker near the open end of each tube. A microphone is placed at the open end of each tube and detects the sound entering and leaving the tube. So this is the diagram of the experiment. The graph shows the variations with tube length L of the time t for the sound to travel along the tube and be reflected back. This is the diagram, the graph, with scatter plot. And look the distance 10 centimeters, 10 centimeters, 10 centimeters, 10 centimeters, 10 centimeters, right? The percentage uncertainty in its time measurement is 9%. The uncertainty in L is negligible. Question A. For L equal 40 centimeters, calculate the absolute uncertainty in T. Right. I would like to using symbol delta T for the absolute uncertainty. Delta T equal 9%. 9% is the percentage uncertainty in T over 100 multiply. We are going to find the measurement value when L equal 40. So we need to find T when L equal 40, when T equal 40 is 1, 2.2. 2.2 millisecond. So the result is 0.198 milliseconds. And after that, rounded becomes 0.2 millisecond. For L equal 40 centimeters, draw the error bar on the graph for this data point only. So we are going to determine the upper limit and lower limit. The upper limit equal T when L equal 40 minus delta plus delta T. It is 2.2 plus 0.2 according to this result. Equal 2.4. And then the lower limit, it is 2. T for T minus delta T, it is 2.0. So the error bar strike line from 2.0 to 2.4, this, the error bar. Draw the line of best fit. If we create a strike line of this, represent of this scatter plot, so we can sketch a strike line from the initial point to the final point, from this point to the final point. But I would like to draw the best fit bar. Of this, there are two at the upper straight line and this one, the lower. Okay. Of the main strike line. Determine using the graph the speed of sound, state, and appropriate unit for your answer. I will using this bullet point 30 and 1.9, while this one is 70 and 4.2, right? to coordinate point 30 and 1.9, and then 70 and 4.2. Right. So gradient of the strike line is T over L, because T is the vertical strike line and L is the horizontally strike line. So it is T2 minus T1. This is L2 minus L1. T2 is this one, 4.2 minus 1.9 over 70 minus 30. And if you calculate, the result is 0.0575. Okay, millisecond over centimeters. Because L unit is centimeters and T unit is millisecond. Now, speed. How about the speed? Speed or velocity is 2L over T, or it is 2 over T over L. That one. So 2 over this number, 0.0575, becomes centimeters over millisecond. And if you calculate this 2 over 0.0575, the result is 34.78 centimeters over millisecond. We are going to convert centimeter over millisecond into meter per second. So one meters is 100 centimeters, and millisecond is 1 over 1,000 seconds. So it's going to be, let's see, 4.78, 10 power minus 2 meters, and this one is 10 power minus 3 seconds. It becomes 34.78, 1 over 10 power minus 1 meter per second. It becomes 347.8 meter per second. Next. Student B conducts the same experiment. There is another student B. Student B conducts the same experiment and analyzes, but places the microphone 10 centimeters to the left of the open end of its tube. Right, so student B create the same experiment, but the positions of microphone is 10 centimeters to the left. Compare with reference to the graph drawn the value for speed of sound obtained by student B to that of student A, the value of speed, right? I have provided my explanation about it. If we compare experiment of student A and student B, student A, student A, the microphone is placed at the open end of the tube. In this case, the sound pulse travels the entire length of the tube. While student B, the microphone is placed 10 centimeters to the left of the open end, meaning the sound pulse travels at distance L minus 10 centimeters, which 0.1 meters shorter than the total tube length. Since the sound is reflected from the closed end, the total distance the sound travels in the tube will be twice the distance from the open end to the microphone. So it becomes 2 times L minus 10 centimeters. So how about their gradient? Student A experiment. Student A experiment has velocity, or better is time equation. The time equation is L over V. Based on this equation, we can determine gradient of A experiment is 1 over V. So what students B? Students B has time equation is L minus 10 over V, and its gradient is 1 over V also. So you may compare that gradient A and gradient B, same. 1 over V, 1 over V. Okay, same one another. How about their speed? Their speed, we can determine their speed through the formula that velocity of A experiment is L over T. Okay, T A, right? And velocity B is 2L minus 10, okay, over TB. It occurs on TB. And regarding the graph, if we compare the graph, so graph created by student B will be lower than strike line of student A. Okay, but they have same gradient. An experiment is conducted to measure the specific heat capacity of water. A mass of water is placed in a glass beaker and energy is transferred from an electric heater. So this is the electric heater and this beaker with water inside. Next, the data collected are mass of water, change in temperature of the water, energy transfer from the electric heater. This calculate the specific heat capacity of water. Right. So the formula is this one: C equal specific heat capacity equal Q over M times delta T. Right. So Q equal this one 16,000 over 16,000 joule over 0.250, this one, mass of water multiply 14.0 in Celsius. So it's gonna be 4,571 joule over kg degree Celsius. Okay, if you change Celsius into Kelvin, it's no problem because the thermometer Celsius equal it change scale. If you change the scale becomes Kelvin, it's no problem because they have same scale, 100 the scale. If Celsius from 0 to 100, Kelvin from 243 to 343. Determine the absolute uncertainty in the specific heat capacity of water. Right. We need to determine first the relative uncertainty, relative, relative uncertainty in M in mass is equal 0.002 over 0.250. The result is 0.008. And then relative uncertainty in delta t. Okay. I'm going to check delta t is this one 0.5. Just now mass 0.002 now. Delta t 0.5 over 0.5 over 14.0. The result is 0.0357. And after that, relative uncertainty in Q. In Q, so let me check. 300 over 16,000. 300 over 16,000. And the result is 0.01875. So total relative uncertainty equal accumulation of this result 0.008 plus 0.0357, 0.01875 equal so total relative uncertainty, sorry, in C, okay, 0.06245. 1, okay, Joule over kg Kelvin. And now absolute uncertainty, the absolute uncertainty, wait, this one, absolute uncertainty, 0.06245 times 4,571.4. Actually, wait, let me see. This one, the first result. Okay, this is 0.43. Supposed to be 0.43, this one. 0.43. 0.43, and it's equal 285.46, rounded to 286 joule over kg Kelvin. Write down the specific heat capacity of water and its absolute uncertainty to the appropriate number of significant figures, right? So specific heat capacity, the specific heat capacity is C equal 4,571.43 rounded to 4,600 joule over kg Kelvin, while the absolute uncertainty in C, this one, I'm going, that is delta C. So delta C, 286 rounded to 300 joule over kg Kelvin. So the specific capacity of water, the specific heat capacity of water C, specific heat capacity of water and its absolute uncertainty is This number 4,600 plus minus 300 joule over kg Kelvin. Outline one source systematic error in the experiment and its effect on the calculated value of the specific capacity of water. I have provided my explanation, this one, that not all the energy provided by the electric heater is used to increase the temperature of the water. Some of this energy is instead transferred to the environment, to the environment around the heater, resulting in a lower temperature change in the water than expected for the given amount the energy input. Right. So if you pay attention, the formula C equal Q over M delta T. Okay. This formula assumes that the energy Q is used to heat the water, but energy loss energy loss in surrounding or in the environment because the calculations value of C, the calculation value of C becomes higher. So C becomes higher than the true specific heat capacity. It occurs uh, because the actual energy absorbed by the actual energy absorbed by water less than energy measuring from the heater. Yeah, that's the reason. Three, the length of a space station is measured to be 100 meters according to observer A at rest in the space station. Observer B is moving at 0.60 c. C is the light speed in vacuum with respect to the space station. Write down the length of the space stations according to Galilean relativity. According to Galilean relativity, that lengths are not affected by relative motions of observer. It means no matter how fast observer B is moving with respect to the space station, the length of the space station remains the same as measured by observer A. So the length of the space stations observed by observer B, it will still 100 meters. Okay, still 100 meters, according to Galilean relativity. Define what is meant by proper length. I have provided my opinion about it, about my answer about this question. This one. The length of an object measured in the rest frame of the object when it is at rest relative to observe, or the length of the object as measured by an observer who is stationary with respect to the object. Calculate the length of the space stations according to observer B with reference to special relativity. Special relativity, right? I would like to start with this one. This is gamma equal 1 over 1 minus square root 1 minus 0.6 square. Okay. Sorry, this is square. And if you calculate, it will be 1 over 1 over 0.8, and it is 10 over 8, 5 over 4, 1.25. Now we're going to find length of the space station. The formula is L equal L0 over gamma. This is L0 is proper length of the space station. The proper length is 100 meters over gamma is 1.25. And if you calculate, it becomes 80 meters, right? So the length of the space stations according to observer B with reference to special relativity is this one, 80 meters. So there is difference. Outline how the result in B part 2 contradict Newton's postulates concerning time and space. Yeah, because in Newton postulates, I have uh, provide my answer here. In Newton postulates, time and space are considered absolute. This means space is fixed and same for all observers. There are two reasons that this means space is fixed and the same for all observers, regardless of their motion. This is the first one. And the second one, uh, this is the first one. So time is the same for, according to Newton's, that time is the same for all observers, regardless of their state of motion. So now this is the first one. Okay, time and space are considered absolute. Time and space are absolute according to Newton postulates. Right. However, according to the special relativity, that according to uh, the second opinion of about the special relativity, that when observer B moves at 0.60 c relative to the space station, the length of the stations will appear contracted 80 meters. So space and time are relative. So according to Newton, that space and time are considered absolute, but according to special relativity, that space and time are relative. They depend on the relative motions of observers. The length contractions of the space station from 100 meters to 80 meters occurs because the length of an object in motion changes depending on the observer's relative velocity to the object. So that's the difference opinion according to Newton postulates and special relativity, right? According to Newton postulate, that time is, the main difference is or the difference opinion about time and space. According to Newton, that time and space absolute, while according to special relativity theory based on Einstein theory, that uh, time and space are relative. Number 4. The diagram below shows two particles traveling in opposite directions above the ground. The velocity with respect to the ground of particle A is 0.6 c, And the velocity of particle B with respect to the ground is minus 0.75 c. C is the light speed, right? Calculate the velocity of particle B according to particle A. Particle B, velocity of particle B according to particle A. It means velocity B to A, right? To find the velocity of particle B according to particle A, we need to use the formula for relativistic velocity addition. And the formula is like this: velocity B to A is equal velocity B minus velocity A over 1 minus VA VB over C squared, right? VB is 1 minus 0.75 C minus VA is 1, 0.6 C over 1 minus 0.75 C times 0.6 C over C squared. It becomes minus 1.35 C over 1 minus 0.75 times 0.6 is 0. It becomes plus here because minus and minus 0.45 C squared over C squared. So it's going to be minus 1.35 C over 1.45. And the result is minus 0.93 C. That one. The particles were emitted at the same time according to observer X at rest with respect to the ground. Another observer Y is moving parallel to the ground. Show that the particles are not emitted simultaneously in the frame of observer Y according to the Lorentz transformations equation. Okay, so we are going to using the Lorentz transformation, and the formula is this one, where I would like to write in here that Txn equal gamma times T minus Vx over C squared. Txn is time in the frame of observer Y. This is Txn, while this one T is time in the frame of observer X. So this Y, this is X. Then X position in the frame of observer X. V, this one V, is relative velocity of Y with respect to X. And what else? Oh, gamma. Gamma is Lorentz factor. Lorentz factor is this one. Gamma equal 1 over square root 1 minus V squared over C squared. That one. While C is speed of light, right? So for observer Y, the time of emissions is calculated according to the formula or according to the rule like this, T AXN. Okay. This is for observer Y. Gamma times T minus Vx A over C squared. And T Vxn gamma times T minus Vx xb C squared. Now subtract TAXN and TBXN. If we subtract, sorry, I'm going to subtract right like this. It's going to be TAXN minus TBXN, and this is delta T actually. Delta TXN because TXN, and it is gamma times becomes minus this one 0, t minus t equals 0 minus becomes it is minus minus phi x minus phi x a, okay, over c squared plus phi x p over c squared, like that. So it's gonna be delta t xn would be gamma times minus phi x a, okay, and this is becomes minus phi x b, right, c squared. This is delta t. It's gonna be delta phi, delta phi, uh, phi delta x, I mean, and then it becomes phi times xa minus xb, okay, c squared, and have it here, gamma times minus phi delta x over c squared, this, that one. So I'm going to add several information that uh, if if xa if xa if xa not equal with xb, then TAXN not equal or unequal TVXN. It means, or meaning, the particles uh, the particles are not emitted. I forgot to add this information. Supposed to be I have to type first. So the particles are not emitted simultaneously in the frame of in the frame of y. Okay, in the frame of y. Right. And the second I would like to writing here that the difference time, or the time, oh yeah, the difference time depends on the spatial separation of x b minus x a. So the relative velocity, and the Lorentz factor. So the difference time depends on the spatial separations xb minus xa, depends on the relative velocity, and depends on the Lorentz factor. This one, the Lorentz factor is gamma, right? What else? Yeah, I think that's enough. Number 5, the space-time diagram gives the city x-axis for observer A, the world line and x and axis for observer B are also shown. When observer A and observer B were at the origin of the space-time diagram, their clocks were synchronized. This is a diagram. Calculate the speed of observer B with respect to observer A. Right. The first step we need to determine gradient or slope of city action. Slope of city action is equal delta city action over delta x action, right? And it is, the action is 1, okay, and this is city action 4 and 5. So delta city action is 5 and this is 4. So that one is 5, 4. And after that, the gradient or slope of x, then it is a delta ct over delta x. This one, okay, 4 over 5. Right. Velocity of velocity of observer B with respect to observer A, we can found using inverse of this gradient, and then comes velocity. Inverse, it means c times delta x over delta ct, and that is c times 4 over 5 or 4/5 c. This for observer A, an event has spacetime coordinates x equal 3 and ct equal 1. Plot the point corresponding to the event on the diagram, label the point E, right? 3, wait, okay, this one, 3. This is the coordinate point E. Okay. And what else? According to observer B, if an E occurs before observer A and observer B meet, justify this statement using the space-time diagram. Right. So we need to find CT xn is gamma times x minus phi t. Right. For gamma, I would like to calculate gamma formula like this 1 over square root 1 minus 0.8 c squared over c squared. And it is 1 over square root divide this 1 minus 0.64 1 over square root 0.36 1 over 0.6 and that is 1.66. This one that is gamma. So we can substitute it into this equation becomes 1.66 times x equal 3 because this one minus this one minus uh sorry, not 50 but phi x, sorry, wrong, supposed to be, this is ct, okay, so ct minus phi x over c, so it's supposed to be 1 because this is 1, ct equal 1 1 minus 0. Phi x is 0.8 c times 3 over c. Right? And this is 1.66 or 1.66 times 1.2.1 minus 2.4. And the result is minus 2.3. Okay. This formula according to Lorentz transformation. So next we're gonna find on uh on the strike line CT extent, we're gonna find minus 2.3. Minus 2.3, this minus 2, 1, 2, 3, this one. And we're gonna create the strike line from E, from E coordinate point E to here. Okay, the strike line, and you may create the strike line using your ruler. Determine the space-time coordinates of the event according to observer B. Right, according to observer B, it means x xn equal gamma x minus Vt. Just now I wrote this formula. It's according to Lorentz transformation, so it becomes 1.66 times 3 because x equal 3 minus 0.8 multiplied by 1. And if you calculate, the result is 3.7. 3.7 on x strike line. 3.7 on this x-axis strike line is 3.312 3, 4, 5, 6, 7. This one, 7, 8, 9. Yeah, this one, 7. Okay. I'm going to using a different color. You may using your ruler to sketch this, right? So we can state that the space-time coordinates, okay, space-time coordinates the space-time coordinates 3.7, this number, comma, minus 2.3. This is the space-time coordinates. Show that the space-time interval between the clock synchronization and the event is invariant, right? So space-time interval we can determine through this formula S squared equal ct squared minus x squared. And this ct is 1 squared minus 3 squared equal 1 minus 9. And it is minus 8. Minus s squared equal minus 8. Invariant. Number 6. An electron is accelerated from rest by a potential difference in a laboratory. Calculate the potential difference required to accelerate the electron to a speed corresponding to a Lorentz factor gamma equal to 0.0 with respect to the laboratory. Right. According to the Lorentz transformation formula, that gamma equal 1 over square root 1 minus v over c squared. Now we are going to rearrange this formula, being is phi is the subject. If phi is the subject, I'm going to arrange become square root 1 minus phi over c squared equal 1 over gamma. So 1 minus p over c squared equal 1 over gamma squared. One more here. So it means phi squared over c squared equal with 1 minus 1 over gamma squared. And then phi squared equals c squared times 1 minus 1 over gamma squared. Right. Next, phi, it means phi equals c times square root 1 minus 1 over gamma squared. Let's we calculate phi. So phi equal c times 1 minus 1 over, if gamma is 2.0, it means 2.0 here. C, it becomes, this is squared, sorry. 1 minus a quarter, so P equals C times 3/4. Okay. Yeah, 4 minus 1. Right. So it's going to be V equal square root 3. 4, sorry, square root 3 half, because square root 4 half here, square root 3 half C. Okay, that one is phi. Next, the relation between potential difference to kinetic energy. AK is, I'm going to writing here that uh, AK or kinetic energy is gamma minus 1 times mass of electrons times C squared. Right, that is kinetic energy. So I would like to using the space that E times phi equal kinetic energy, which E is elementary. This is the elementary charge. So the implication phi equal kinetic energy over E. So kinetic energy is this one. So it becomes 1 over, sorry. So phi equal 1 over E times gamma minus 1 me C squared. So and E equals, so it becomes, I'm going to calculate with, so phi equal 1 over gamma minus 1 is gamma is 2, so it means 2 minus 1. Mass of electron is 9.11 times 10 power minus 31, while C is 3 times 10 power 8, okay, over E, 1.6 times 10 power minus 19. So phi, if you calculate phi equal 0.511 and phi. Okay. So this is the result, 0.511. A baryon is moving with respect to both the laboratory and the electron. Laboratory reference frame momentum of the baryon 450 mega electron volt per C. C is speed light. Energy of the baryon is 1,100 mega electron volt. Electron reference frame energy of the baryon 1,700 mega electron volt. Determine the momentum of the baryon in the reference frame of the electron. According to the relations of relativistic energy and momentum, that the total energy we can determine through this formula that E squared equal P squared C squared plus M squared C power 4. So we can rearrange this formula becomes E squared minus P squared C squared equal M squared C power 4, or M squared C power 4 equal E squared minus B squared C squared. Or I would like to write things like this. MC squared equals square root E squared minus B squared C squared. Right. Uh, so it becomes, or wait. So not using the square root. Better if I will find, I'm gonna find m squared c power 4. This is e squared is 1,700, or 1,100, I mean, 1,100 mega electron volt. This number. Squared minus 450 squared. PC is 450. And if you calculate and round it, it becomes 1,000 squared. Right. Now we're going to determine the momentum of the baryon through this formula that P squared C squared equal E squared minus M squared C power 4, according to this equation. So P squared equal E squared minus M squared C power 4 over C squared. So P equal square root E squared minus M squared C power 4 over C squared. P equals square root. That's a baryon, so I'm going to using this energy, this 1,700 squared. M square, I'm going to use in this 1,000 squared over C squared. Mega electron volt. So it becomes P equal, if you calculate, this is, the result is, wait, 1,374 mega electron volt, okay, per C. Okay. That is the result. Supposed this is squared, because this is squared also. What else? Part B done. Okay. Number 7. Explain the path followed by like near massive objects. I have provided my explanation about this question. Mass and energy curves or wraps space-time, and this curvature dictates the motions of objects. Instead of thinking of gravity as a force pulling objects, general relativity views it as the effect of moving along curved space-time. This warping of space-time is responsible for various phenomena, including orbits, gravitational lensing, time dilatation, and the motion of planets and stars. Next. An experiment is to be conducted on Earth to investigate gravitational redshift. A beam of gamma photons of energy is 14 kiloelectron volts. is to be emitted and then detected at a height of 10 meters above the emission. Calculate the expected change in the frequency of gamma photon due to the gravitational redshift. Right. Uh, to determine, to find the solutions or determine the gravitational redshift, we are going to calculate first the frequency of photon. The frequency of a photon we can determine through the formula F equal E over H. Okay. This is the frequency. E is photon energy and H is the height. Right. So I'm going to I'm going to find energy first. Energy, the photon energy. The photon energy based on this information is 14 kilo electron volt. So we're going to convert kilo electron volt, the electron volt into joule. 14 kilo electron volt, it means 14 times 10 cube electron volts. One electron volt, it equal 1.602 times 10 power minus 19 joule. So it can be 14 times 10 cube times 1.602 times 10 power minus 19 joule. And it becomes, the result is, if you calculate 2.2428 joules, sorry, times 10 power minus 15 joules. Right. Next, substitute into this formula. So F equal 2.2428 times 10 power minus 15, okay, over 6.626 times 10 power minus 34. And if you calculate, the result is 3.38 times 10 power 18. This number is Planck constant. So Planck constant is 6.626 times 10 power minus 34. That is H. Next, we can determine frequency of gamma photon due to the gravitational redshift based on the formula of gravitational redshift. The formula is delta F. Delta F equal F times G. This is the frequency. This one, the frequency of a photon times delta H over C squared. This is gravitational force. Delta H is this 110, and C is light speed. 3.38 times 10 power 18 times 9.81 times 10, this one, over 3.0 times 10 power 8, like speed squared. And if you calculate, the result is 3,687 hertz. approximate, yeah, you can approximately becomes 3,700 hertz or 3.7 times 3.7 times 10 cube hertz. Number 8, a solid disk initially at rest, rose without slipping down an inclined plane. The disk has radius 5.5 centimeters. The length of the inclined plane is 1.5 meters. This is the diagram. And then the time taken for the disk to roll down the inclined plane is 0.96 seconds. State for disk, the relationship between linear displacement L and the angular displacement theta. Right. When a solid disk rolls without slipping, the relationship between linear displacement L and angular displacement theta we can writing as L equal the radius, okay, the linear displacement, the displacement L equal radius times theta. Okay, L is linear displacement, R is radius of the disk radius, theta is the angular displacement. If the angular displacement is the subject, we can rearrange this equation being theta equal L over R, or theta, or angular displacement equal linear displacement over the disk radius. Calculate the angular accelerations of the disk. Well, okay, I need more space. We can calculate through this formula, and the formula is alpha equal to theta over t squared. This formula is formula of rotational kinematic equation. So alpha is angular acceleration, t is time, while theta is the angular displacement. Yeah, yeah, the angular displacement. Right. So we need to determine theta first. Okay. So theta is according to this equation that theta is 1.5, L is 1.5 meters, and radius is 5.5 centimeters. So 1.5 meters. We need to convert centimeters to meters, becomes 0.055 meters. And if you calculate this, the result is 27.27 radians. Next, substitute theta, the theta values into this formula, alpha. So alpha equal to times this number, 27.27 over t is 0.9. According to the previous information, 0.96, 0.96 t squared, 0.96 squared. And if you calculate, the result is 59.186, rounded to 59, and the unit is radian per second squared. Next, the disk and a ring with the same mass and radius are released from the top of the slope at the same time. Explain without numerical calculation which one will reach the bottom of the inclined plane first, right? I have provided my explanation. The moment of inertia determines how easily an object can rotate. For a solid disk, the moment of inertia is the formula is half m r squared. M is mass and r is the radius, the disk radius. While for a ring, it is m r squared. The ring has a larger moment of inertia because all its mass is concentrated at the outer edge, whereas the mass of the disk is more evenly distributed. Because of both the disk and the ring are rolling without slipping, they convert potential energy into both translational and rotational kinetic energy. The disk, with a lower moment of inertia, converts more potential energy into translational kinetic energy, which affects its speed, and less into rotational kinetic energy compared to the ring. It means that this accelerates faster. It's faster. It has accelerates faster. So the conclusion: the solid disk will reach the bottom of the inclined plane first because it has a lower moment of inertia, allowing it to roll faster compared to the ring with the same mass and radius. Number 9, a planet orbits around a star in an elliptical orbit as shown below. This is the diagram. At point A, the planet is closest to the star. This is the star, and this is planet. The planet at point A. And at point B, it is furthest from the star. This is point B. As the planet orbits the star, it has a moment of inertia, I equal mr squared, where m is the mass of the planet. State what r represents in this situation. I have provided my answer. This r represents the distance between the center of planets and the star's center at any given point in orbit. So this is r. This is r when the planet's in point A, and this is RB when the planet position on point B. Next, show using conservations of angular momentum that the linear speed of the planet is greater at A than at B. So when the planet on positions A, the linear velocity greater than when the planet at point B. Right. So the angular momentum, we can determine the angular momentum. Okay. The angular momentum we can determine through the formula L equal mr squared, mr squared. This is momentum of inertia, mr squared, times v over r. Okay, momentum of inertia times angular velocity. This is angular velocity, this momentum of inertia. And we can simplify, becomes m r phi because r squared over r equal r. If phi, the subject linear speed, phi is the linear speed. R is distance between the star and mass of planet. So if phi, the subject, this equation being L over m times r, like that. So look, if r greater, if r a less than r b, you may evaluate on this diagram that r a less than r b or r b greater than r a. So the implications on the velocity, if 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 r a on this fraction, the less of r, the greater of the linear velocity. The less of the radius or the distance, it means the greater of the linear velocity. So the implication is the implication that phi a, okay, linear velocity of on point A uh, is greater than linear velocity on point B. Yeah. Based on this formula, okay, calculation, right? Suggest why in this situation the magnitude of the linear momentum of the planet is not conserved. Linear momentum of the planet is not conserved, whereas the magnitude of its angular momentum is conserved. I have provided my answer for this question. Linear momentum P is not conserved. You know that linear momentum formula is P equal m times phi, right? So this is not conserved because velocity depends on the radius, the distance between planets. Linear momentum p is not conserved due to the difference of linear speed. Okay, and the linear speed affect due to the radius or the distance, whereas angular momentum L gravity angular momentum formula is L equal mRV. But angular momentum gravity acts towards at the center and therefore does not create a net torque. So there is no implication from the gravitational. So that's why the angular momentum is conserved. The pressure P and volume V diagram represent Carnot cycle for an ideal monoatomic gas. Okay, this is a diagram. Pressure versus volume. I mean P and V. Right. Show using the first law thermodynamics that during the process from A to B, energy is supplied to the gas. So from point A to point B, it's going downward. Right. First law thermodynamic is expressed as, wait, I'm going to run. It's expressed as delta U equal Q minus W. Which are delta U is change in internal energy of the gas, Q is the heat added to the gas, and W is work done by the gas. For an ideal gas undergoing an isothermal process, the change in internal energy, delta U, is equal to zero because the temperature remains constant. So we can state that delta U equal zero because the temperature constant. When when the velocity of B greater than the velocity of A, if you look this diagram, the velocity B, okay, greater than the velocity in point A. So the values of natural, if velocity B greater than velocity on in point A, it means the values of the natural logarithms. I'm going to writing here better. Learn of velocity B over velocity A. It is positive number. I have to clean this area first. So learn VB over VA, that is positive number. So it means the implication that learn, if positive, learn VB over VA, that is greater than zero because it's positive number. So W result also, the W also equal the positive number. Okay. If W equal a positive number, it means the implication that W greater than zero. Recall that delta U equal Q minus W. So it mean if delta U equals zero, it means Q minus W is equal zero. So Q equal W. If W greater than zero, it means Q equal W, which greater than zero. So we can state that this one, Q equal W greater than zero. The following data are given. This data show that the volume of the gas at D, volume of gas at D is about 4 times 10 power minus 3 meter cube. It means this is VD, right? To formula, adiabatic formula is PV power gamma equal constant, which gamma is adiabatic index. Gamma adiabatic index gamma is 5/3 for monoatomic. This is for monoatomic ideal gas, right? So PV is PA times VA gamma, power gamma equal PD times PD power gamma. Right? If Phi is the subject, we can rearrange this. This equation becomes Phi power gamma equal Pa times Va power gamma over Pd. If gamma equal 5/3, it means Pd power 5/5 is equal Pa times Va power 5/3 over Pd. Let's continue here. So Vd equal Pa times Va power 5/3 over Pd. And all of this fraction is power 3/5 this. And now substitute this value. These values are 4.3 Pa pressure on A. This one pressure on A 4.3 times 10 power 5 multiply this one Va volume on A 2.2 times 10 power minus 3 power 5/3 over Pd, this one pressure at D 1.7 times 10 power 5. All of this fraction power 3/5. That one. So if we calculate, the result is 0.0033839 rounded to 3.84 times 10 power minus 3. The unit is meters. So this is the solution. Calculate the efficiency of this Carnot cycle. Efficiency formula, efficiency equal 1 minus times in D over times at A times at D over times at A, which times at D over times at A, it equal pressure at D multiply volume at D over pressure at A volume at A. So it becomes efficiency becomes 1 minus PD VD over PA VA. Substitute the number 1 minus PD is 1.7 times 10 power 5. VD is this one, 3.84. 10 power minus 3 over 4.3 times 10 power 5, 2.2 times 10 power minus 3. Divided becomes 1, divided equals 1. And if you calculate, you're going to find 1 minus 0.69. And the result is 0.0033839. 31. In percentage is 31%. Number 11, an ideal fluid is traveling through a pipe that has a large diameter at one end A and a smaller diameter at the other end B. Okay, this is the pipe outline why the speed of the fluid is larger at B than at A. Okay, B has a smaller diameter than A. I have provided my explanation. This you may copy or adding something into this opinion. My explanation next. The fluid enters the pipe at A at a rate of 2.3 kilogram per second. The smaller radius at B is 1.2 centimeters, and the density of the fluid is 900 kilogram per meter cube. Calculate the speed of the fluid at B. Okay. To calculate speed at B, I'm going to using this formula that VB equal M over rho times area B. Okay, which VB is the velocity or speed at B. M is mass flow rate, and rho is the density of fluid. This is the density, this one, density of fluid. And AB is area of B. Okay. All right. I will find area B first. That is pi r squared. And R is this one, 1.2 centimeters. So R equal 1.2 centimeters. Convert to meters becomes 0.012 meters or 1.2 times 10 power minus 2 meters. So pi times 1.2 times 10 power minus 2 squared. And the result is, and I'll convert first, 22 over 7, 1.44 times 10 power minus 4. And this is calculate 4.5257, 10 power minus 4 meters squared. Okay, and next, substitute into this formula. PB equal mass 2.3, this is the mass, over 900, because rho is 900, times 4.5257, is 10 power minus 4. Next, calculate 2.3 over 900 times 4.5257. The result is 0.00056467 times 10 power 4. And if we calculate, it becomes 5.0 meters per second. So the speed at fluid B is the speed fluid at B is 5.65 meter per second. Number 12, a mass is attached to a horizontal spring. The mass is displaced so that it is at position x0 from the equilibrium. The mass is released from rest and starts oscillating. After one complete oscillation, the amplitude is measured to be x1. The Q factor for the system is 200. This is the Q factor. Show that x1 over x0 is about 0.98. Okay. So the relationship between the initial amplitude x0 and the amplitude after one oscillation, this x1, that it is can be given by the formula of this formula x1 over x0 is equal e power minus pi over q, which q equal this one, 200. Now, if q equals 200 and substitute into this formula, it's going to be x1 over x0 equal e power minus pi over 200. And it's going to be e power minus, if this is this pi, 22 over 7 over 200. The number is, the result is 0.015700795. That one. Now, on in my calculator, e power this number, the result is 0.9844, rounded to 0.98. Next. The spring is now connected to an oscillator that drives the oscillations. So this graph. The graph shows the variations of the amplitude of oscillations with the driving frequency. Draw on the graph above how the amplitude would vary for a system with a much larger factor. With a much larger factor, so the resonance peak will be and taller and narrower. So the graph will be taller and narrower. This is because a higher Q factor indicates lower damping. So the system can sustain larger amplitudes at the resonance frequency. I would like to sketch this. Okay. Okay. Or like this. Yeah. Right. Okay. So the resonance peak, its peak will be taller. It will be taller than this the original one, and narrower. It's because the higher Q factor indicates lower damping. Okay, next. I think clear. Justify the curve drawn in the previous question. I have provided my explanation. This, so you may copy. I will not reading. You may copy my explanation or adding something. Number 13. The thin lens equation model rays passing through the center of a lens as undeflected outline. Why a ray passing through the center of the lens can be assumed to be strike. I have provided my answer about this. Okay, so no need for me. I think no need for me to add my explanation. This information is enough for you. That's from me. All right, let's continue. A ray diagram for a thin diverging lens is shown. This diagram. The lens forms an image of the object. Draw the image and the rays from the object to show the formations of the image. All right. So I would like to sketch first the strike line from the object towards the lens. Like this. Wait. Okay. And then from lens towards F, like that, strike line. And it forms the image here, the image located here. Okay, that's the image. Next, we are going to find the another ray. Okay, and then after that, from the object. This is a strike line actually. So you need a ruler to create this strike line. Okay. Sorry. It's supposed to be towards local the focal point. All right, that the rays. Let's continue. Estimate the linear magnifications of the lens. So we need to find the object distance and the image distance. Object distance, this the object distance. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. While the image distance, 1, 2, 3, 4, 4.5. The image distance, 4.5. So the magnification equal, wait, this is 10, this is 0.5, the magnification equal image distance over object distance, 4.5 over 10, 0.45. Explain how spherical aberration arises for real lenses and how it can be reduced. I have provided also my briefly explanation about this question. Okay. This is my explanation. Okay, students, I think we can move to the next question. An optical compound microscope in normal adjustment is composed of an objective lens of focal length 0.82 centimeters and an eyepiece lens of focal length 2.9 centimeters. An object is placed 0.91 centimeters from the objective lens. The image is formed at the near point 25 centimeters from the eye. Show that the angular magnifications of the microscope is about minus 90. Yeah, it's about minus 90. Right. Great. Okay. Firstly, I would like to find how to calculate the distance of image through this formula that 1 over uh, f object is equal 1 over d object or distance object plus 1 over the image distance. And if the image distance, the subject, this formula becomes 1 over f object minus 1 over the object. And it's equal 1 over the image equal 1 over f object is 0.82 minus 1 over 0.91. And if you calculate this fraction, calculation 0.1206, that is 1 over the image. That means image distance equal 8.29 centimeters. That is image distance from the objective lens. All right, so 8.29 centimeters from the objective lens. Now I would like to show uh, the sketch like this I have prepared. This one. Look that this is the positions of the object. So this is the distance of the object, and then where is 8.29? 8.29 is from this one. 8.29. Okay, from this point to here. This is the object, and the image, according to information, that 25 centimeters from the eye. So 25 centimeters. This 25. Wait, 25 centimeters. This is the eye here. Okay, this is the eye, and this the 25 centimeters from 25 centimeters. This is eye lens. This is objective lens. This objective lens, and this is the eye. Uh, yeah, this is the eyepiece lens. This one, eyepiece lens, and this is the objective lens. So from the eyepiece lens to eyes is 25 centimeters. So the image occur on our eyes. Think clear? Let's continue. The final image through the eyepiece is magnified. State two other characteristics of the final image. I have provided also virtual and inverted. Number 15. Explain why the refractive index of the cladding in a step index optical fiber is only slightly less then the refractive index of the core. But I have provided my opinion about this question, this one, and I would not reading this. You may copy. Okay. Okay, students, let's move. Part B as well. I have provided my opinion, my answer about this. Explain how a graded index fiber reduces the effects of waveguide dispersion. I have provided this. Okay, you may copy or you may add your opinion for this explanation. All right. C. An optic fiber has an attenuation per unit length of 1.1 decibel kilometer, decibel per kilometer. Determine the maximum length of the fiber so that at least 4.0% of the initial power transmitted reaches the end of the fiber. Right. It means we are going to find, if determine the maximum length, we need to find L. Okay. 1.1 decibel kilometer is the attenuations for an optic fiber attenuation, right? The formula for attenuations of light in optical fibers, we can use this formula says P out equal P in times 10 power minus alpha L over 10. Or we can rearrange becomes P out over P in equal 10 power minus alpha L over 10. Alpha is the attenuation coefficient, 1.1. This alpha, 1.1 decibel per kilometer. P out is the power at the end of fiber. And then P in is the initial power. L is length, length of the maximum length of fiber. Right. The desired fractions of power at the end of the fiber is 4%. At least 4%. It means this is the desired fraction of power. So it means P out, the desired number, maximum, because this is the maximum length. So it means uh, P out over P in is equal to 4.0%, or in decimal, it is 0.04. So we can substitute this number into this equation that 0.04 equal 10 power minus 1.1 L over 10 because alpha is 1.1. And then we can use the logarithm rules that log 0.04 equal log 10 power minus 1.1 L over 10. Okay, next. Continue. I need more space for 8. And I would like to clean this area first. Right. Let's continue. And based on logarithm rule, we can write things like this, that log 0.04 equal minus 1.1 L equal log, that's 1 over 10, is log 10. Or we can replace the position becomes minus 1.1 L over 10 log 10 equal log 0.04. Log 10 equal 1. So minus 1.1 L over 10 equal log 0.04 is minus 1.39794. I'm going to move here. So minus 1.1 L equal 10 multiply with this number comes minus 13.9794. So it means L, or the maximum length, is minus 13.9794 over minus 1.1. And if you calculate, the result is uh, positive 12, because minus over minus 12.7085 rounded to 13. And the unit is kilometers. Number 16, an X-ray image is taken of a patient leg. Part of the beam, ray A, passes through soft tissue only and leaves the leg with an intensity IA. The remainder of the beam, ray B, passes through soft tissue and bone and leaves the leg with an intensity IB. The diagram shows a simplified model of a cross-section of the leg. So if you look at this diagram, that ray A passes through soft tissue, and then ray B, I0, ray B passes through bone, right? So intensity A and intensity B. The following data are given: width of the leg 20 centimeters, width of the bone 9 centimeters, attenuation coefficient of tissue 0.13 per centimeter, attenuation coefficient of bone 0.59 per centimeters. Determine the ratio IA per IB, right? To determine the ratio IA per IB, we need to use the Beer-Lambert law. It says that, I'm going to write it here, I, intensity after passing through the material, equal I0. I0 is intensity, initial intensity. I0 times E power minus mu. Mu is attenuation coefficient, and times X. The X is the thickness of material, right? So for ray A passing through 20 centimeters of soft tissue only, ray A, we can determine the intensity of ray A to the formula that IA, intensity A, equal I0 according to this formula, E power minus U soft times X soft. So mu soft is 0.13 per centimeters, while X soft is 20 centimeters. So it's going to be IA equal I0 E power minus 0.13 multiply 20 becomes I0 E power minus 2.6, because 0.13 multiplied 20 equals 2.6. Next, for ray B, this is for ray A. For ray B, passing through 11 centimeters of soft tissue and 9 centimeters of bone. So it means IB, IB equal I0 E power minus mu, mu soft times X soft plus mu bone times X bone. Okay, becomes I0 E power minus uh, mu soft, and it means 0.13 multiply 11 because x soft here in IB is 11 centimeters plus this is 0.5 mu bone is 0.59 multiply this one x bone 9 centimeters, right? So it becomes I0 e power minus, if you calculate this, is minus 6.74, right? And after that, if you calculate next the ratio, if you calculate the ratio, IA, IB, IA is I0 e power minus 2.6 over I0 e power minus 6.74. Divided becomes 1. So it becomes e power 6.74 minus 2.6. E power 4.14. Now, in my calculator, I have calculated e power 4.14, and the result is 62.85. That one. Next. The same leg is to be imaged using ultrasound. State what is meant by acoustic impedance. By the acoustic impedance, okay, this is the acoustic impedance. Impedance is a property of material that describes how much resistance an ultrasound wave encounters as it passes through the material. It is given by the formula. I would like to write in the formula. The formula is Z equal rho times V. C is the acoustic impedance. Rho is the density of the material, while V is the speed of sound in the material. When the ultrasound passes from soft tissue to bone, some of the ultrasound is reflected. The fraction of reflected ultrasound is given by this one. The fraction Z2 minus Z1 squared over Z1 plus Z2 squared, where Z1 is the acoustic impedance of soft tissue and Z2 is the acoustic impedance of bone, right? So acoustic impedance of soft tissue and this one acoustic impedance of bone. The following data are given: density of soft tissue 1,100 kg per meter cube. Speed sound in soft tissue is this one. This are the data. Calculate reflection ultrasound reflected at the soft tissue bone boundary, right? To calculate ultrasound reflected, we need to find one by one. C1 first according to this fraction, this formula. So we need to calculate C1 first. So for soft tissue or C1, the formula is rho soft multiply V soft. Okay? The density multiply speed. And rho soft is 1,100 multiply 1,600 according to this information. This one, and this one. And if you calculate, the result is, I have calculated, this is the result, The unit is this one, while Z2 is this is for bone, this is for soft tissue, and C2 is for bone. It means raw bone multiply phi bone. That's the information. It means 1950 multiply phi bone, this one. And if you calculate, I have calculated this 7,995,000 kilogram meter square second. Right. So it means ratio is C2 C1 squared over C2 plus C1 squared. So substitute this number. If you substitute, it's gonna be like this. This number over 7,995,000, 176,000, and then it's gonna be, if you calculate this squared, I have calculated this, and the result is 0.639. It's going to be 0.408, rounded to 0.41. That one. Set one advantage and one disadvantage of using X-ray over ultrasound for a medical image. I have provided my uh, opinion. This one, you may copy, or maybe if you have different opinion, you may using your opinion. As well as one for disadvantage, we can continue to the next option. Explain with reference to the protons how nuclear magnetic resonance NMR imaging can distinguish between bone and soft tissue. I have provided as well my explanations about this. I think clear. The diagram shows the extreme positions of star A 6 months apart as seen from Earth. The black dots are the fixed positions of distant stars. The horizontal scale is in arc seconds. So this is the diagram. It's in arc seconds. Okay, distant stars. Show that the distance to star is about 10 BC, right? So it means I'd like to from the star to the star are about 0.18 arc seconds. So, right, so the parallax angle is half of this arc second, half from this star to this star. So it means the parallel equal 0.18 over 2, 0.09 arc second, uh, arc second, like that. This is the unit. And how to find the distance by parallax formula. is 1 over, okay, 1 over P, that equal D. So we can determine D, okay, or distance is 1 over this number 0.09. And the result is 11.11 PC. Okay. PC or parsec, parallel second. The parallel second, I mean, right? Calculate the ratio distance to star A, distance from Earth to the Sun, right? The first step you need to find distance to star A. Distance to star A, it equal 35. Wait, sorry, no, not yet. That's the result. 11. According to this calculation, that 11 uh, parsec. This approximately becomes 11 parsec, right? 11 parsec, we're going to convert from parsec to meters. So this is 1 parsec, 11 parsec times 3.26, 6.26 light years, like years, like that. This is like years, okay? Because 1 parsec equal 3.26, 3.26 light year. That's 1 parsec. And then 1 light year equal 9.46, is 9.46 10 power 15 meters. Okay. So multiply 9.46 times 10 power 15 light year per meter. Right. This is distance from distance to star A. And if we calculate, the result is, I will calculate this 35.86 like here, because 11 times 1 like here, multiply 9.46 in like here per meter. And if you calculate this number, 35.86 times this one, and the result is 339.24 times 10 power 15. And in a significant figures, 3.4, 10 power 17 meters per unit. This is the distance to star A. Now, the distance from Earth to the Sun, distance from Earth to the Sun is 1 astronomical unit. 1 astronomical unit is 1.5 times 10 power 11 meters. So the ratio is the comparison between this number and this number. 3.4, 17 over 1.5, 10 power 11. And if you calculate, the result is 2.267, 10 power 6, or 2.3 times 10 power 6. That one. Next. I have provided my answer for this one. Star B is part of constellation. Outline what is meant by constellation, by a constellation. This my explanations. You may copy this one or you may add something into this explanation. Okay. Now this one. The analysis of the stellar spectrum of star B shows that it has a surface temperature of 9,900 Kelvin. Star B is main sequence star with a luminosity of 25. This is a symbol of the luminosity of the sun, L, the sun, 25 L sun. Outline how the temperature of star can be determined from the stellar spectrum. We can determine through wind displacement law. Wind displacement law. Okay. It says that lambda max equal B over T. Lambda max is the wavelength of which the star's emission is strongest. This lambda max. B is wind displacement constant. Uh, the number is 2.898 times 10 power minus 3 meters Kelvin. While T is temperature. Okay. The surface temperature of star and the unit in Kelvin. So how you will determine the temperature? So just rearrange this formula being T equal 2.898 times 10 power minus 3 over lambda max. How about the temperature? Temperature, of course, in Kelvin. Also, these questions I have provided my explanation. This my explanations. But before you copy these explanations, I would like to inform you that my first explanation. This is the second. This is the second one, the third one, and this is the summary. This one, the last one is the summary. This one, right? So I would like to show you the relation between mass and luminosity. The final state in the evolutions of a star. It depends on mass and luminosity of the star, and the relations luminosity and mass of the star. I would like to use in this space. The relation is L is proportion to m cubed. Right. So luminosity of the star proportional for m cubed. Okay. Mass of star cube or mass equal L power one third. According to the information on this problem, that L equals 25, so M equal 25 power one third. So if you calculate, the result is 2.9. So mass is 2.9 of mass of sun. This right. So this the explanation. So this is 2.9 mass of sun. Is approximately 2.9. When the star B has mass of approximately 2.9 mass of the sun. And as well D, part D, I have provided my explanation this. Okay, another star in the constellations is a separate variable outline the reason for the variations in brightness of the star. This is my outline. So this is the first, the second, the third, and this my summary. Okay. Now, 18. The cosmic microwave background CMB radiations is observed to be largely isotropic, with a temperature of about 2.76 Kelvin. Explain how these features of CMB provide evidence for a hot Big Bang model. I have provided my explanation, my opinion about this question. One, you may copy this explanation, or you may add something to this explanation. Okay. Next, a galaxy is observed to have a redshift 0.01. Hubble's constant can be assumed to be 70 kilometer per second MPC. Calculate in unit MPC the distance to the galaxy. Right. To calculate distance, the galaxy, we can use the Hubble's law, and it says that V equal H0 times T. So if we are going to determine distance, it means we can rearrange this formula becomes D equal V over H0. Okay. With V for velocity of a galaxy, H0 for Hubble constant, this one the Hubble constant, and D for distance to the galaxy. Now, before we determine, before we are going to find distance, we have to determine first the velocity. So the velocity we can determine through the formula velocity equal c times c. C is redshift and c for speed light, while v is velocity. So it means v equal v equals 0.01, the redshift is 1, multiply the speed light 3 times 10 power 5 kilometer per second, and it's equal 3,000 kilometer per second. And after that, substitute this number into this formula. D equal 3,000 kilometer per second over this number, H0, 70 kilometer per second MPC. So 3,000 over 70 is 42.86, and then second, kilometer divided by kilometer, and the unit is MPC, rounded to 43 MPC. Next, determine the age of the universe in seconds, corresponding to the above value of Hubble's constant. We call the Hubble constant is 70. If you answer to at least two significant figures, right? So I would like to writing first that 1 MPC, that is 3.09 times 10 power 19 kilometers. And we are going to convert the Hubble constant H0. I would like to convert that H0 is 70 kilometers over second MPC. Okay. So it becomes one MPC is this one, so 70 kilometers over uh, over two. MPC is this one uh, over sorry 309 10 power 19 kilometers. This second because this is second. Okay. So and the result is if you divide 70 divided by 3.09 is 22,654 10 power minus 19 s power minus 1 per second, rounded to 2 point, 2 point in significant figures 2.26 10 power minus 18 per second. So if we are going to find uh, the age the age of the university through formula that's T0 equal 1 over H0, it's going to be T0, the age of university, 1 over H0 is 1, 2.26, 10 power minus 18 per second. And if you divide, calculate, the result is 0.4425 10 power 18 second. In significant figures, 4.42 10 power 17 second. Next. Explain how the observation of uh, type 1a supernova provides evidence for an accelerated expansion of the universe. Okay, so I have provided this is my explanation. You may copy or you may add your opinion into this explanation. 19. In the core of a red giant star, helium fusion occurs for about 1 billion years before the star enters the next stage of its stellar evolution. However, a super-red giant fuses the helium in its core in about 1 million years. Deduce the cause of the difference in times. I have provided my explanation about this question. One. Okay. Next. Some super-red giants evolve into supernova. Elements heavier than iron can be produced through the R process in a supernova. Describe the R process and the conditions in a supernova that allow the R process to occur. I have provided also this, my explanation, my opinion. Right, let's move to the next number. Show using Newton's universal law of gravitation that the rotational speed of stars near the center of the galaxy, v root, okay, speed rotation, is proportional to the distance of its star from the center of the galaxy, galaxy D. Assume the mass density near the center of the galaxy to be constant and the galaxy is spherical. All right. To find the rotational speed v root, right, we need to use the concept of circular motion. The gravitational force provides the necessary centripetal force for the star's circular orbit. Uh, yeah, for the circular orbit around the galactic center, and we're going to using uh, the formula of Newton's. It says F equal G times mass. This is mass enclosed. I would like to ENC, okay, times N over D squared. And it is equal, okay, it's equal M times V root squared over D. Yeah. Okay, V root is this one. Okay, speed of the rotational speed of stars. Right. Now we are going to substitute if mass enclosed equal rho times 4/3 pi d squared. D cube, I mean, that m enclosed, mass enclosed, okay, d cube. Substitute into these equations, it's going to be g times this one, rho 4/3 pi d cube m, this m, over d squared equal m v root squared over d. M divide becomes 1, and this one as well. So it becomes G rho 4/3 pi d equal V root squared over d. And after that, we can rearrange becomes the rotational speed squared equal d times d rho 4/3 pi d squared. So rotational speed becomes square root G rho 4/3 pi d. That's one. Okay, 21. There is a graph. The graph shows rotational speed was originally predicted to vary with d. This d axis and this is the vertically is the rotational speed axis. Scale to the observed relationship on the same axis. Okay, so we are going to sketch if so this if we look the result that the root is square root 0 4 sorry 4/3 pi d. So actually this is the slope or gradient of the diagram. So it means for the larger d, the gradient, the graph will be like this. Okay, the straight line here. That's the graph. Outline one current hypothesis which supports your answer to the previous part. Okay, I have provided as also my explanations, my briefly explanations about this question. This one. Okay, I think this is clear.